So hi, I'm Archit Chandak, and today I'll be taking you through the DFM analysis of a deep drawing process. So let's start. Uh, so deep drawing is a sheet metal forming process in which the sheet metal blank is radially drawn into a forming die by the mechanical action of a punch, and therefore it is a shape transformation process with material retention. So you see, these are the products, the beverage cans. This is an engine part. These are cups. So these are all made from deep drawing. So this is the schematic outline of the deep drawing process. The punch exerts a force vertically in this direction, and this is the red colored blank, and these are the blank holders, and this is the die. So initially the blank is in this shape, and then it takes this shape, and finally after multiple passes it takes the shape we want. And so this is not restricted to just cylindrical shapes. We can have a square shape blank or a conical body, etc. So the another important thing we should know during deep drawing is the LDR, which is the limiting draw ratio, and it is the ratio of maximum diameter of blank to the punch diameter for drawing without failure. This is very important. And the limiting draw ratio LDR is capital D by D, and this is the initial blank diameter, and this is the final piece, small d. And this is the typical failure we observe during deep drawing. So if we exceed the LDR, we have this type of failure generally. So basically, coming to the important part which we want to know is the design for deep drawing. So this is the rules based DFM analysis for the deep drawing process. And basically DFM analysis refers to design for parts for ease in manufacturability, and these rules can be incorporated at the design stage to improve the efficiency of the process. So the type of material, the first rule we give here is the type of material used. And so the percentage of elongation property or ductility of the material is an essential quality for materials to be used for deep drawing. The second is the material thickness. Slightly thicker materials can be gripped better during the deep drawing process. And also we should know that the thicker sheets have more volume and hence can be stretched to a greater extent. However, the drawing force will increase with the sheet thickness. The third is the blank size and shape. The blank that are too large can restrict metal flow. The geometry of parts can also affect the ability of metal to flow during deep drawing process. And another thing is the blank holding force. So the control of the blank holding force enables control of friction on the flange during deep drawing process and significantly influences the quality of drawn part. And so the greater blank holding force may lead to the tearing of the flange, and while inadequate blank holding force may lead to wrinkling of the flange. And another thing is the punching speed, very important, because sufficient punching speed allows time for materials to flow through the tool. Corner cracking will always occur if press speed is fast in the deep drawing process. And then the draw radius, so we talked about it, the LDR, limiting draw ratio. So this is same thing. Radius on the draw die where the material flows through should be optimum, because if it is too big, a die or punch radius can result in wrinkling, where it is too small, a dry radius would create cracking at the bottom radius of the drawn part. And then we have the draw bead height and shape. They should be selected properly to control metal flow and gripping pressure in the deep drawing process. Draw bead height and shape can cause materials to bend and unbend, at the entrance, and to create restrictive forces going into a tool. So increasing pressure will exert force on the material, and it will create more restraint on the material which is going into the tool. And then we have the tool surface finish and use of lubricant, and which is like when the blank is pressed inside, the die surface finishes and the lubricants are important because they reduce the friction between the tool surface and the metal being drawn. So basically, let me show you this here. So the if the friction is less, it is a smoother drawing process, and which will allow materials to flow through the tools more easily. And then we have the N and R values. The N value is also called the work hardening exponent, and it describes the ability of the material to stretch, and which we use in the Holloman hardening law. And then we have the R value. Basically, this describes the anisotropy, and it is a plastic strain ratio. It refers to ability of the material to flow or draw. So yeah, higher, if we have higher NNR values, we'll obviously have higher drawability, because this indicates the ability of the material to flow. And also blank sizes and shapes that are too large can restrict metal flow, and the geometry of the parts affects the ability of metal to flow. So press speeds must allow time for materials to flow. And number of passes required, so it is not a single pass process, it is a multiple pass process. And therefore after say one pass, we have to anneal it, and then other part is passed again. So since it is a multiple pass process, this also calls for the requirement of various presses. And generally the capacity of the press is dictated by the first pass. And then we have the temperature. So higher temperature allows for deeper drawing and more stretching by decreasing the flow stress. So this is very obvious, and increasing the ductility of the sheet metal, and while reducing the viscosity and the effectiveness of the lubricant. So basically it increases the drawability, high temperature. And then we have the standoffs. So standoffs, basically they maintain a given space between the drawing surface and the binder. So too much binder pressure can be overcome using standoffs. And if the standoff gap is too small, the material will be pinched tightly between the drawing and the binder surface, reducing its ability to flow freely. And if it is too large, the material will wrinkle during the compression. So yeah, this is it. We talked about many rules for the DFM analysis of the deep drawing process, and I hope it helps. Thank you.